Hello everyone and welcome back to Whitehorn Racing. Today we'll show you how to go from this to this. Since some have asked us, we decided today to show you how these finned copper shims are made. Clearly, for many, this explanation will be superfluous because they'll know how to do it. Some may need it. However, it takes a little patience, but it's relatively simple operation. We must start well, though. You need something like this, which is a compass point that is put on the drill press, and by loosening this Allen key, it allows you to distance the cutting edge from the fulcrum in order to make it with the desired diameter. Now, where do we start? From a rectangle. A plate of cooked copper. Mind you, it must be cooked copper because it must be soft. You must be able to press it. So don't make hard wrinkles and shorts in case you have small deformations. It can be found in shops that sell. There aren't many, to tell the truth. The shops that sell metal, and it comes in very large sheets, 1 meter wide, so you have to buy it in strips. I'm usually happy with having made 13 centimeter strips from which 8 12.5 centimeter pieces are cut out from, because that way you get to 1 meter in this way, which is a 12 by 13 sides, which is fine. For the 200 it's a bit small, but that is fine anyway, and for the 125 it's more than enough. I try to skimp because copper is expensive. It's an expensive material, so in order not to curl it immediately, you need to have a wooden board like this one, in which the plate is stopped by means of screws with a washer. Then we want to shorten the explanation, sum it up. You tighten it. It's fixed in such a way that it remains firm. Then the tip is mounted on the drill press, and the central hole is made to arrive at this point of the machining. It's necessary to start from the hole that corresponds to the cylinder barrel, because it's the most difficult to make. And based on this, then all holes are made for the studs. The hole will be made just narrower than necessary, so that it can be widened with one of these flap wheels of the right diameter. There are a few on the market. I also made some for my tests in short, and this hole must be made smaller so that you can remove some material with this wheel, so that there is no burr left, because cutting it with the flag tip leaves a small relief. A smear is formed. Here, I left it here. You can see that the edge is not perfect. You can then remove it with a cutter such as this, placing yourself flat. But it takes time. It's best to just keep yourself slightly undersized and then spread it out. On the other hand, it's very important to have old cylinders and pistons to use them as a template. Now you see, this piston is a 63.8. I use it for 63, and it's a bit tight. So what should I do now? With the drill, I slightly widen the hole until the piston skirt fits perfectly. It absolutely must not stay loose. It must go right. Here we go. Let's see where we are. The piston goes right through it. Now, let's place the copper plate with the precise center hole in its place. After that, using a screwdriver, I really tighten this now, so I'll show you. You take the piston, use a 63.8 by 63 because it's necessary to avoid that the edge of the shim protrudes inside the cylinder. Since the centering is good, but is not accurate to the 10th of a millimeter, if you make it the whole of 63 or 63.2 only, you risk that the edge will end up where it shouldn't. On the other hand, keeping 7 or 8 tenths more than the diameter of the cylinder makes sure that this will not happen. Now, the piston is perfectly planted on the ring. The cylinder is then put on. Clearly this is a 177, but for the 200 it's okay. You do the same thing, taking care, however, to make the hole less centered and make sure that there is less copper on the side where the air arrives and a little more towards the exhaust. Then the cylinder is fixed to the axis with 2 clamps, taking care not to let the piston escape from its position. Yeah, at this point it's used. I've already made bolts. I have several depending on the cylinder types. Or you can use sharp studs with a bit of tape to center them. Better if you have a bolt. This here is a bolt from a 127 cylinder head. Clearly the bolt or the one you use to mark must be pointed and must be fit perfectly into the hole, because if there's play in the hole then it will mark in the wrong place and the holes will not match the studs. To beat without causing disasters, you need to help yourself with 2 hammers. You hit once and then mark. Now, the 2 clamps can be removed. The template cylinder is also removed, and as you can see, now with a drill press with a 7-bit, in this case 8 for the 200, you drill. So here's the perforated gasket. Here's a bit of a smudge. If there is, before you can go over a little, with the cutter. The razor blade doesn't last long, but well. After that, I usually take it on a flat piece of iron. I do it this way to make the edges flat. Now, let's go back to the drill press and with a conical tip, with a conical cutter, we touch the edge of the hole, also to be able to remove any excess more easily. And recommendations. Now I'm doing it with my hands directly here because this is an old drill with a 3-phase motor. with capacitors and very little powerful motors. So if something happens, it stops immediately because the drill has very little strength. In fact, to make the circular holes, I don't use this one, but a much bigger pillar drill than I have on the other side. If you have a powerful drill press, never put your hands near it because it's extremely dangerous. You have to remount the plate on the wooden plank and do this thing having mounted it on the plank because it's very easy to get hurt. This is a drill that stops right away. See, it barely manages to start, so there's no danger. Let's see if we got it right. There we go. Now, the simplest operation to do is left, that is with scissors. To cut the sheet metal, you have to do something like this. Clearly, you have to do it carefully. Leaving it whole, it could actually, the radiant surface is greater this way, but in the end, the air could not touch the last fin of the cylinder. All this bending a little could act as a screen. That's why it breaks them in this way. Now this here is mounted like this. The air comes from here, so it's okay to be a little narrower on this side because it's the coolest part, and a little wider on the other side. Then you clearly put a head on top and remove the edges with 2 bolts. You take a head, lean on it and mark the corners to be removed. This must be removed first. First it must be made round and then the cuts are made. Clearly on this side and above the fins can be shorter because it's the part most affected by the flow, to the advantage of the part below and the part towards the body, let's say. It must be said that I have been doing these things for several years and I have certainly benefited from them. However, when we tried to talk about it on the forums, we were a little teased. But now Pinasco is making them and VMC also gives it with the kit. So there are things whose functionality has also been noted by others. Basically, it serves to remove heat in the peripheral part of the combustion chamber, which is the one where auto ignitions originates more easily. Of course, these same procedures can be replicated for small engines. The procedure is always this: you need to have a cylinder to make the template, put the piston upside down, all in the same way, secure it well with the clamps, and it comes out perfectly. Now, a further explanation about the thermal conductivity of copper and the effect of these thinned thicknesses. Copper has a thermal conductivity coefficient almost double that of aluminium, and also of pure aluminium, because alloyed aluminium has worse thermal conductivity coefficient. Having a high thermal conductivity coefficient means that the heat applied to one end of a rod here in a part of this shim spreads rapidly towards the periphery. It's not that it gets hotter, because I heard some fanciful considerations about it. Therefore, the heat transmitted to a part, obviously the one taken between the head and the cylinder, and above all the one exposed to the flame front, will be more easily transmitted up to the edges of the copper plate, and therefore more easily removed by the airflow. Among other things, it's tests that you can do very well. Take an aluminium wire, a copper wire, and an iron wire. Place the soldering iron on the one end. Take a strand of this length and touch the other hand with your fingers. You'll notice how much the copper one will burn easily than the others. It's the same thing that happens here. So the heat is moved more easily. It no longer stays hot. It does not form hot spots on the contrary. It inhibits the hot spots. And keep in mind that this type of solution was also used in aftermarket kits for air-cooled two-stroke engines in the 70s. So it's already in practice. Now, clarification. This whole artifice is a harbinger of positive effects on these engines, which are relatively crude. Then it's clear that if we were talking about racing engines, but with specific powers of a completely different order, then it becomes more important that there is no passage where self-ignition can take place. We're talking about liquid-cooled engines that don't have the problem of ours. In particular, in these engines, the best possible solution is to have the head recessed with slight interference in the cylinder, so that there are no thin spaces, even minimal gaps in which self-ignition can originate. From this point of view, the height of the first band is also of great importance. Here too, there is a controversy though. Again, for this reason. So the L-shaped band gives rise to precise faces, but it itself gives rise to a passage between the piston crown and the band. The first band, if it's too low, also gives rise to passage. So the best solution is that in this case, the first band is rather higher, but not L-shaped. Of course, we speak even on kart engines which have this lightweight recessed head solution. Engine close to 400 HP per liter, light years from ours, so rest assured and get this gasket to work. If you like this video, leave a thumbs up and share it with your friends. Remember, White One Racing is not a workshop, but an amateur sport association that works on engines only for sport purposes and only for its associates.